So what I'm going to conclude with is give you a bit of an outlook on essentially fancy non-parametric modeling. And this is really just something to whet your appetite. Unfortunately, this class, well, there's so much more that I could and should have talked about. On the other hand, I probably put way too much content in the class, into the class anyway, so anyway, so this is really just to show you where you can take these ideas from what I just told you. So, how can you extend topic models? So, one thing that you can do is, we assume that this topic vector is given by a Dirichlet distribution, but actually it's unreasonable to assume that any pair of topics is equally correlated, right? So you could actually try to learn that correlation in its own right. That gives you something called a correlated topic model. You could have a hierarchical structure of the topics. That's a bit of an alternative to that, because that immediately also induces correlations between topics or subtopics or sub-subtopics. You can build entire trees, and then the inference usually becomes reasonably nasty. Then the next thing is, of course, documents are not really bags of words, so you would probably want to build a really nice language model, and then marry that with, a topical analysis of the document. So what you're doing through that is you're starting to move more and more towards actually doing, natural language processing, doing decent document analysis, where you find out what the document is about, what the various pieces in the grammar, which roles they play, how they interact with each other. And I think there's actually still a lot of work to be done to really scale this. Because a lot of the work in that area, at least a lot of work in academia, is on thousands, maybe tens of thousands of documents. On the other hand, you can get essentially billions of pages, or large scans of books and so on. And you would really want to actually use all of that information to come up with a very good model. And then, those structures, so there's a lot of nice work here these guys did. In many cases, for instance, for documents or for users, you actually have context. Sorry.
Yeah. So going back to the idea of scaling this up. So in these more structured cases, we have things that are correlated and hierarchical.
Yeah.
So what is it? Just what is it? What's the new roadblock that makes them not scalable?
Okay. So. Well, in some cases it's simply that we started scaling up this stuff a couple of years ago, and we just haven't gotten around to have a go at all of those models. The other thing is that usually, I don't know why, but in some academic communities, it's so much cooler to build a new model as opposed to make something really work. And that's very frustrating, because you then get those papers which define the next latest cool model on a tiny toy dataset that nobody cares about. In industry, you're very much at the other end. I think sitting somewhere in between would be much more sane. The other thing is that sometimes those structures simply mean that some of the inference algorithms that you used before will break. In some cases, simply the inference algorithms that are proposed right now, nobody knows how to scale them up to a very large amount. So for instance, sequential Monte Carlo, how to parallelize it really well. If you solve that problem, you've solved a very important issue. So this is at the moment still very much open, unsolved, and wouldn't it be nice if we could figure it out? So that's basically why this really hasn't been done yet. And there are still a lot of theoretical guarantees to be derived. Basically, at the moment we make certain approximations, and they're not really terribly well understood. Like the fact that we essentially synchronize things lazily while each individual machine does sampling means that, of course, we only have an approximation to the correct model. The question is, is this approximation okay? How large is the error that we're introducing? There are some parts where you can argue that it's good. For instance, you can essentially argue with concentration of measure, where you say, well, if I have 1 billion users, then, well, updating a few users isn't going to change things too much. But that needs to be formalized. And sorry, yeah.
And then on that note, I mean, when you're talking, it seems like there's a dichotomy between these toy problem sets that people are dealing with, and then like 80 billion users.
Yeah.
And I'm kind of wondering, at what point, because like I don't have 80 billion users worth of data, but I might have more than 1,000. So like, at what point does it switch and?
Okay. So that's a good question. So first of all, you would be surprised how much data you can actually get if you just talk to people and you ask around and so on. And this is often, let's just say, a competitive advantage of research labs, that they know where to get the data from. So in some cases you may have to work with the people who have the data until they trust you. And that's a sunk cost.
What I mean is not that you can't get 80 billion, I'm sure you can get that data. What I mean is if the problem you're looking to solve is only on the order of a couple of 100,000, and the theoretical guarantees for some of the things you need for 80 billion don't kick in yet, but it's still too expensive for the old way.
So the good news in a way is that whenever those large scale approximations don't hold, you can be more wasteful with CPU cycles. So you can be more conservative in terms of the approximations that you make. So in a way, reality comes to your help, in the sense that, whenever the guarantees aren't quite so tight, then, you just spend more time and, do it more carefully, more slowly. So therefore, the big worry isn't at the medium scale. The big worry is actually, how do you make approximations that are not too horrific at the very large scale. There's still a lot of stuff that's not really resolved there. Yep.
On a different axis rather than the amount of data, another question I had is that you mentioned, oh, hey, we'll just do 1,000 iterations. Well, that's highly
heuristic. Yes.
How do you even think this is at all sensible?
Okay, good question. So what you do is you can look at things like log likelihoods. You just look at where they converge. You can take smaller amounts of data. You then take, for those smaller amounts of data, where you can sometimes solve the problem exactly, you actually compare whether you are getting the same solution quality as in the exact solution. So basically, you study controlled situations where you can actually do everything perfectly, then you compare. So that's one of the things that you do. Now, let me just briefly go through some of the models, but actually I see it up in the back, so I don't know. Do you want to make any announcements?
No, I didn't.
Okay. Good. So basically, the correlated topic model, this is one of the first things that people did. So if you look at the Dirichlet distribution, you can just model which topics are really relevant, but you can't really get the correlations between them very well. So, you expect you see documents about sports and health, but not about sports and politics so much. And so what you do is basically, rather than having a conjugate, you use a logistic normal as the prior. So basically, something that's similar to the Gaussian process that we did. The problem is that now you lose conjugacy, so you cannot do all those nice integrating out tricks that I showed you, and the inference is really nasty. So, well, you get a more beautiful model, but you can't really use it very well. To give you a bit more of an idea, so here's what you get, for the topic distributions for a Dirichlet. So here you basically have something that's fairly uniformly spread out. Is something where you really emphasize one topic over the others. Here, where you assume that they're all quite closely always occurring in the same mixture. Here, you really don't know exactly what's going on at all, so everything's fairly smooth. So these are priors of correlations of topics that you would see. But what you can't do is stuff like this, where you actually have strong amounts of correlations, for instance, between And that's what you get if you just have a look normal prior on the topics. So there's not enough time to go into a lot of details here. This is really just a high-level overview to give you some idea of, if you need to do a modeling approach and whatever I showed you so far doesn't quite fit, here's where you would need to look for more. And yeah, you get fairly nice things where, those topics are neatly correlated. Or to squint, you will see that, those correlations make sense. You get a similar thing if you then actually look at the world emissions model, and that's a different data set. It's fine. Now, what you can also do is, you could, assume that, it's not just, independently drawing your topics, but maybe you go through some directed acyclic graph. So after all, for LDA, you go and pick a document, and for that document you pick a mixture. You could say, well, you could pick a first mixture that then gives you a second one, and so on and so on. So you can have additional edges, and you can go crazy on paper. In practice, this is about where it stops being practical. But it's always beautiful if you can write the more general model. And what this will give you is, a different way of encoding correlations between topics. So, who has ever been to Japan? Okay, so you've probably seen a Pachinko parlor, right? So it's basically those Bernoulli boards where you put steel ball on top and then it falls down, and at some point ends up at the bottom. And so this is where the name Pachinko allocation comes from, because essentially you model your genetic process accordingly. So that's why it's called a Pachinko allocation model. There's a very nice paper in JMLR on that. And then you can get really cute stuff like this. So these are basically topics. These are the nodes one level up, and you can see that, at one node. So first of all, so this is about papers, so I don't know, it's probably about 10,000, maybe 100,000 papers. But, each paper has, abstract-based paper approach present. So each paper has to have this. But then there are those papers which go about data mining, clustering, databases, and information. Right? But then you could have a paper that does information, web servers, and networks, or networks in parallel and performance and distributed, and so on. So you can essentially, get better correlations between some topics, and that are then, reused in some context. So this gives you a better understanding of, the content. And then, you could have hierarchies. So, where you basically say, well, first pick a word, and you get more specific, and then you get more specific yet again. And, well, this is what's called a hierarchical topic model, and you see that, all the stop words end up on top. And then as you go down, it becomes more and more specific. So these are papers from NIPS. You can have engrams. So in that case, basically, the current word determines, in addition to the next topic, what the next word is. So this way you can, get correlations like the White House. And then, engrams is a little bit misleading because they only really deal with bigrams. There's a lot of work along those lines. Some of it is then similar and solves very similar problems, but yeah, differences in techniques, but you can get stuff that's reasonably meaningful. And so you can see that these types of word combinations are actually interesting stuff. Okay. So, in other words, if you don't like your bag of words, here's your fix. The good thing is it's a little bit like Lego. You take, an engram model, and maybe you decide, okay, you want to have it hierarchical, and by the way, I don't quite like so much, the Dirichlet distribution, so I would like to have, a correlated topic model. And you throw everything together. At some point it becomes really expensive to solve, but in theory you could combine these bits and pieces. And that's then what essentially good modeling for a problem is all about, to decide which of those pieces you actually need in order to solve, the problem well enough. Another thing that's quite useful is, so if you have documents, you usually have, side information. So for instance, if I have a document, I know which server it came from, when it was retrieved, when it was written. I know a lot of, structure around it. I know maybe, the rank of the document. If I have scientific papers written by some authors, then, for instance, if you know that I wrote the paper, you can reasonably well infer, what the paper is about. By just, looking at all my past papers, you know that. Now, if I write a paper with somebody else and they also have a certain track record, you can reasonably well guess what a joint paper might be all about. You can use this information, and that's actually very nicely done by David Widner and co. And so they get, nice what they call upstream condition. Now it turns out you can actually do a similar thing downstream. So for instance, if you know attributes for words, you can use that to infer for a new word where you just know some attributes of it, what it might be about. Okay. That could, for instance, be in the case where you have like WordNet. Let's say in WordNet you know that certain words are related, so therefore if I know the topic distribution for one word, I know what the related words are all about. Or if I have, two corpora in different languages, I have a dictionary, and I can, if I have solved the problem for one, I can solve it for the other one. And yeah, you can use labeling and so on as well. So, to give you a bit of an idea. So, here's for instance what we did. So this was on what's called the Europarl corpus. So it's basically the European Union, because they have so many different languages. They release a lot of their legal documents in all the languages, right? Because of course none of the membership countries would ever accept that their language is not represented, right? And this was, I think, in a case where they had 20 languages. Okay, so we picked, no, sorry, that was 20 topics, sorry. We picked 3 words, namely democracy, demokratia, and demokratie, basically 3 different languages, Spanish, French, English. And what you can see is that, by and large, those things are reasonably well correlated. Not entirely, because maybe, those words are not always used exactly in the same context, but we used that corpus without any alignment. So in other words, we didn't have the equivalent of a Rosetta Stone, where you just take 2 documents, you say, well, they actually mean the same thing. In that case, it's easy, because you can really say, well, they have to have the same topic distribution, but otherwise you don't. You can use fancy things for recommender systems, and you can basically go wild in the modeling. Yep.
For models such as this that are obviously rather complicated, how do people actually go about designing inference procedures?
That's an excellent question. And okay, so here is where I hope we will be in a couple of years. I hope that in a couple of years it'll be a situation where you can go and write down that model in some specification language, and then you have a compiler which compiles it into code and optimizes. And as it optimizes data layout, optimizes machine partitioning and all that. This is where I hope we will be in a couple of years. Right now, it's a lot of matter of experience. So once you've done this a few times, it gets easier. And you know that certain tricks, certain approximations will work again and again. So the easiest way how to learn modeling is to, solve such modeling problems. And as you keep on doing that, you will become better at actually solving them. So to some extent, what I've made you do in all the assignments is, solve modeling problems. Now, some of them have relevant templates in it, which you might later on encounter if you work in academia or in industry. And that practice will help you then, I hope at least. It's unlikely you will encounter the very problems that I've given you in the assignments, but at least you might encounter something related. Now, it's not quite all doom and gloom. I mean, some people have started building libraries. So for instance, there's something called GraphLab, and that is very well on its track to become a very nice distributed latent variable inference library. There is a very nice piece of work that at the moment, well, at least for the supervised part, yeah, unfortunately that team is essentially evaporating at Yahoo, where basically you could specify things in a domain-specific version of Scala, and then you would have, you know, the standard database compilation tools to optimize this. There's a very high chance this product will be reborn in some other company, and just stay tuned. You will see some probably very nice things happening in a year or two at a much larger scale. But at the moment there is no really easy tool set to really convert problems into code. There are toolkits that make it partially easier. So for instance, our LDA toolkit is highly scalable, but it's probably the opposite of what I would call user-friendly. Because we basically use it as an experimental platform. So right now you still have to do actually a lot of work yourself. So yeah, that's the unfortunate current situation, but I hope it will be quite different in 4 or 5 years from now. Any other questions on that? Okay, good. So I'm going to conclude with just very briefly what's called the Chinese restaurant process. And that should help you a little bit address the issue of, you know, basically, you know, we don't know the number of clusters, we don't know the number of topics. Can we actually estimate them automatically? Right? So I'm going to show it to you mainly as a procedural tool, as opposed to actually a mechanism, you know, with all the basic non-parametric theory behind it, just because that would be a class in its own right. But here's basically the idea, right? So, you know, you might ask, you know, how many clusters should we really pick? And, you know, well, the radical solution is we say, well, let's just pick, you know, prior over an infinite number of clusters. And let's, you know, let the data sort it out. So, you know, if you look at this ratio here, this looks awfully familiar, right? It's basically, you know, actual counts plus smoother divided by total number of counts plus sum of the smoother. Right? That's after all what we went through here on a couple of, basically in the first hour. Now what you can do is you could say, well, you know, maybe you just let the number of possible outcomes go to infinity, in which case, while keeping that sum fixed, so then this contribution here, so the smoother for a specific instance goes to 0. And since we require this to stay constant, we get this here. So in addition to that, what you now need is that there's a non-zero probability to create a new cluster. It's just, you know, this coefficient alpha divided by total number of counts plus the smoother. So this should actually be alpha rather than some for y prime, alpha y prime. So in other words, what we now have is a process by which the probability of picking something that I've already seen is proportional to the number of times that I've seen it already. Probability of picking something new is proportional to a constant. So P of new is alpha over those counts. P of existing is, you know, previous counts. So the nice thing is then this Chinese restaurant metaphor. And the idea is basically, you know, you have a Chinese restaurant with an infinite number of tables, and people sit down at those tables, and then the probability of sitting down at the table is proportional to the number of people that already sit at the table, and then there's a constant for, you know, picking a new table. And there's a lot of really beautiful research in that context, and yeah, you can basically go wild on that. Basically take one of probably Mike Jordan's advanced seminars, and he'll be talking a lot about this. Or yeah, Jim Pittman, or a lot of other cool people around here. Yeah. So Any questions right now? Because then I'll actually go and use this stuff for document analysis. Yep.
So for clustering, it seems that it's nice to figure out how many clusters you actually need. But
Right.
in this case, it seems like the richer so the bigger clusters get
Yes.
more and more samples, which you might not want in practice because you want to have some sort of balanced clustering. So how does that fit in, or how do you
Okay.
deal with that?
So first of all, things aren't quite that bad because, I mean, the probability of a new cluster, you know, after having so many instances, is actually dependent of how many clusters you've already generated. So it's basically, you know, alpha over n plus alpha. So the expected number of clusters is sum over n equals 1 to infinity of this, or, you know, up to n. And that's basically order log n. So that basically means that, you know, you will get order log number of instances, many clusters. That may be a little bit too drastic, and so that's why Pittman and Yor developed what's called the Pittman-Yor process. And in that case, what you do is you don't quite pick that number, but you basically make this, you know, the probability of a new cluster grow a little bit with how many instances that you've seen. And then you can get essentially, you know, rather than log n, you get something like order, you know, n to the alpha, n to the beta, where beta is some exponent less than 1. So there's not enough time to go into that in a lot of detail here, but if you're interested, look for what's called the Pittman-Yor process. And you can actually use similar models for instance, describing how preferential attachment processes work on, you know, social networks or internet graphs, and that has its own name, but it essentially has a similar preferential attachment process. Okay. So I'll conclude with a few very brief examples. How can you, for instance, use that for, you know, evolutionary clustering? So in other words, you know, you have a time series of objects like news stories, and occasionally stories come up and some disappear. I want to keep track of the clusters automatically. What you do is you then use this Chinese restaurant process, and whatever we had at time 1 is then used as a prior for time 2. Basically, I just use the counts, use them as a prior for, you know, who ends up there at time 2. Users go there, whatever, okay. And then I use that, you know, maybe nobody's had time at that table, and I use it as a prior for time 3, and I keep on going. So this way, you know, a new story that shows up, I mean, there's a good chance that, you know, we'll see it again tomorrow, but if at some point I don't see any evidence of that story anymore, I forget it. I can have a longer history, where you look at basically longer range, and then you can actually, you know, do all sorts of funny things about, you know, how long stories last, and so look at a paper by Ahmed and Singh if you want to know about that in detail. Now, I'll conclude with something, just what you can do about user modeling. So let's say I want to buy a camera, right? Then, well, you know, at some point I think about the camera, and then I go and, you know, start searching for it, and then at some point I might actually decide to buy it. Right? And so the question is, you know, when should you show ads? So who suggests we should show ads here? Well, nobody really, right? Because, I mean, that's just going on in my mind. Should I show ads here? Well, I mean, unless I have a mind-reading advertising system, which would be a little bit creepy. Well, here's a good time because, well, we actually see that, you know, I start searching for this stuff. If it's there, which is the typical case, I don't know how many times this has happened to you, but it happened to me quite a bit that, you know, you end up, you know, being shown the ads for, you know, a camera after you've actually bought it. That's really game over. I mean, here's, okay, would you like to have a camera case, a memory stick, and, you know, maybe, you know, a lens So basically, turns out you can actually do this model. I'm going to quickly skip over a lot of detail which we don't have time. I'll just show you an example of what you can actually do in reality. So these are two users, random users, I don't know the gender. These are the topics that are automatically extracted. So that's by using actually a topic model where everything is time dependent, so the topics can change over time, user interests can change over time. There's a global interest distribution for the topics. So everything is time dependent. And, well, let's look at this user. So, I mean, in terms of naming the topics, I think women, men, dating, singles, personal, seeking, match, calling it dating is pretty reasonable. Anyway, this person is heavily interested in dating. At some point, maybe after a bad date, starts worrying about his health. Right? Then at some point discovers baseball and dating is not so important anymore. Right? So that's number of days, so that's a bit more than a month. This person here, diehard baseball fan throughout. Except that maybe after a week or so he discovers he doesn't have much money. About a week or so later he starts searching for jobs. Interest in baseball takes a bit of a dive, and he was never really interested in dating. So that's the kind of stuff that you can get automatically with the right model. And of course that's why you care. And I think I've really used up essentially really all the time. Now, if there should be any time left on either next week or the week thereafter modulo the presentations, I can easily talk about a lot more things in a lot more detail. Just let me know what you want to hear. It's been fun with the class so far. Yeah, and I think it's late in the day, so if you have any questions, let me know. Otherwise, good luck for next week. Don't forget to tell Darko whether you're going to present next week or the week thereafter.